We're group 11 and our topic is titanium dioxide and our member is I'm Memphis and our member is Noah, Larry, Chloe and Angelina. So first we'll introduce what titanium is and then we will introduce how to synthesize this material and then we will for material quality scale up, we have to introduce how to characterize titanium dioxide and then we will introduce how it is used in our daily life. So first, for introduction, we have to talk about whether you are painting at your wall and using sunscreen. There are chances that titanium dioxide is included. So what it is, where this come from, why it is so widely used in our daily life. Titanium dioxide is a fine powder. It is whitest and brightest pigment. It reflects visible light, scatters, and absorbs UV light. Titanium dioxide most commonly occurs as a mineral eliminate and sometimes rutile. Then the black raw material will be sent to countries that and extract to become usable titanium dioxide. Australia was the world's largest ilmenite ore producer with about 1.3 million tons of production. Titanium dioxide scatters visible light, which make it all color even and strong, so it can be used to brighten and straighten the cover of production, such as paint, paper, and plastic. This feature also can be used to increase sustainability. It extends the lifetime of plastic, wood, and metal. Titanium dioxide can also be produced as finer powder to be transparent and more efficiency to scatter and absorb UV light. It makes it an ingredient of sunscreen. Titanium dioxide can absorb light energy irradiated from the sun, release electron and become positive charge. It gives us strong power to decompose virus and pollutant. So there are some important properties for titanium dioxide. The first is reflectivity. Titanium dioxide can protect product from aging, but how? We can see the graph by adding titanium dioxide as an ingredient or just paint on the surface. Most of the radiant can be reflected. Less energy absorbed by substrate means that harm from radiation and heat. It can keep our product from aging and increase the sustainability. Then the second property is UV light absorption. Titanium dioxide is a material that can absorb UV light efficiently. The graph in the right-hand side is the extinction coefficient. It's an index to show the material absorbed light. By the spectra of extinction coefficient, we can learn that the line with proton energy above 2.3 eV to 4.6 is the best for absorption line. It shows that line with wavelength lower than 267 can be totally absorbed. It is why it is a good material to help people against UVB and UVC. Titanium dioxide has band gap of 3.2 eV. When a light with wavelength lower than 384 strike on the titanium dioxide, a free electron and a hole can be created and drop to N-type layer and P-type layer respectively. That is how titanium dioxide plays an important part in dye-sensitive solar cell. The mechanism can also be used to air purification, wastewater treatment, and sterilization. When titanium dioxide gets energy from radiation, the free electron can be react with water molecules from hydroxide radicals and react with oxygen to form superox radical anion, and then will react with harmful virus and pollutant in the air or water and decompose them. Here's an example. And next are synthesis method.
And the thinner this is the advantage and the disadvantage of the titanium dioxide thinner method. And the solder method, it can make fine particle, but it needs long process time. And the hydrothermal method can make small particle size uniform distributions. And the microemulsion method is easy to transport and store. And the CVD method is simple layered film from device, but the deposition rate is not high. And the industrial scale. Several industry produce titanium dioxide. Here is one of the introduced and the technology used to scale up the productions of titanium dioxide. Here is the company in Japan. They have used the advanced soldiers technologies to produce titanium dioxide on the on a large scale. The pro- productions capacity of titanium dioxide is around 157,000 metric tons per year. And here is the general scheme of how to do the soldier techno- technology to obtain thin film and products of titanium dioxide by the soldier method on an industry scale. For the sold technologies, there are two ways to obtain titanium dioxide thin film. For drone technology, there is one way to get titanium dioxide power with the purity of 99.9% and a higher conversion yield of about 98%. Thanks.
Okay, and the next part, I want to talk about characterization of titanium dioxide. Titanium dioxide can be identified from the composition, thickness, chemical transformation, structure form. The characterization methods are classified by microscopy in the differentiations such as SEN, TN, and XRD. For spectroscopy like XPS, UVBs, and the EPR, and the SPB, and the Raman, require to measure the magnitude of infected piezoelectric constant use AFN, and some fancy techniques like synchrotron radiation with micro XRF and micro XANES, and the in situ SRPXRD. And the next slide. This page is a reference that we find. These papers are majorly talking about the characterization of titanium dioxide. And these figures are from paper 1. Paper 1 combined metal like as barium titanate with titanium dioxide to improve the photocatalytic performance and to achieve excellent piezo photocatalytic efficiency. From the XRD, you can see titanium dioxide have two different phases. The identified pieces are marked with green colors, and the black dots are ascribed to the different phases of titanium dioxide with annotates and rutile. Raman spectroscopy is an effective method for characterizing structural symmetry of materials. From Raman spectroscopy, we also can see the peak of barium titanate and the titanium dioxide. The morphology and the structure of products are observed by SEN and TEN, and we can see the titanium dioxide mainly consists of uniform strain nanostructures. The article absorption property and the backend energy of titanium dioxide can be analyzed by using UVBs. And the paper 2 inserts a barrier tiny nanolayer between titanium dioxide nanorod and a gold nanoparticle in order to enhance reactive oxygen species, also called ROS. And we can use ESR spectroscopy to verify the speculation that the insertion of variant nanolayer will contribute to the enhancement of ROS generation. From the figure, we can see the final ROS product of hydroxide and oxygen were detected. And from the paper 3, paper 3 introduced oxygen vacancy can effectively enhance the photo-induced charge separation and the visible light absorption performance for titanium dioxide photocathode anode. The oxygen vacancy was generated through treating the pristine titanium dioxide photoanode with hydrogen under different temperatures. The treated samples are denoted as titanium dioxide -O-T, where T represents the temperatures. In the paper, two different temperatures experiments. For example, 200 and 315 and 400 and 415 degree. And the paper said when temperature is 400 degrees has better performance. From XRD, La treating titanium dioxide show a typical rutile phase. SEN imager reveal the formation of nanorod array structure. The treating titanium dioxide is here a strong EPR signal at a G value of 2.002, which can be attributed to electron trapping in oxygen vacancy. And next panel will
I will continue the characterization part. So from the fourth paper references, which is from the JHS paper, show the modification of the titanium dioxide into two types, which are titanium dioxide nanorods and titanium dioxide nanoparts, which can photogenerate the charge spread and transfer more efficiently, resulting in outstanding PEC of activity. So in that paper, there are ECM, XRD, and the Raman spectra to characterize the titanium dioxide. And the other method is the photoilluminescence or the PL emission spectroscopy. So this used to reveal the dynamic on the migration and spiration of the photogenerate electron in holes in titanium dioxide catalyst. And the next paper, for the fifth paper reference from the Environmental Science and Technology, they use the advanced nanotechnology, which is the synchrotron micro X-ray fluorescence, or the micro XRP, and the micro X-ray absorption spectroscopy, to track the presence and chemical speciation of the titanium within the plant tissue in two-dimensional maps. And from the image A and B, this is the micro XRP, are to map the titanium in the vascular system of the electrode treated with the titanium dioxide nanoparticle with the three color of the micro XRP. And then by using the micro XA and yes, and in image C and D, so it will find the titanium was in the form of the titanium dioxide nanoparticle with the roots of the wheat plants and their crystalline. And for the last paper references from the crystal growth and design paper, there use the in situ PXRD or the in situ powder X-ray diffraction to know the formation mechanism and the crystal growth of the titanium dioxide with in the higher temperature, high pressure fluid were studied using the hydrochloric acid and also the sulfuric acid. So the in situ synchrotron radiation power X-ray diffraction reveals that the pure rutile titanium dioxide nanoparticle can be formed using the HCl in the figure A as the additive and also use the hydrochloric acid in the figure B.
So the next slide we will discuss about the semiconductor company and some regard of the commercial product that use the titanium dioxide. So the first company from the Samsung Electronic, they use the titanium dioxide for the chip scale package of the LED light. So the technology provides the considerably higher light efficiency, energy efficient, long lasting, and also the environmentally friendly. The second company is the Micron. They use the titanium dioxide for the multi-chip package because titanium dioxide will increase the speed and also the power efficiency. The third one is the Murata manufacturing. They use the titanium dioxide for the ceramic capacitor, and the ceramic capacitor are placed in the electronic device for the interior of the car. And the next one is the Intel Corporation. So they use the titanium dioxide to create a big chip and usually placed on our computer as the motherboard chip. And the next one is the Ricoh in Japan. Uh, this company are developed the solid state of the dye synthesizer cell. The next one is the Keyfashion in Hong Kong. They develop the titanium dioxide wireless charging pad. And then the Sino-American Silicon Incorporation and also the Dysol in Australia, they use the titanium dioxide to create a solar cell and also the dye synthesizer cell.
And now we're going to talk about the application of the titanium dioxide. And we are going to talk about semiconductor field and in daily life. So first of all, we are going to talk about flexible OLED. The flexible OLED, we have a lot of different possibility of the titanium dioxide application. And and here we're going to talk about we're using the titanium dioxide to make the electrode. So the traditionally we fabricate the OLED using the ITO as an anode and the glass as a substrate. And here when we going to make our OLED become flexible, so we need a flexible substrate like a polymer. And usually we're using the Ag nanowire, silver nanowire as our main material. But here's the problem. Here's the problem of the Ag nanowire and the polymer because they have the bad morphology surface and also they have the bad thermal stability. So we're using to drop some titanium dioxide solution on our silver nanowire, so make them become a core and shell structure. And by this way, we can make the our electrode become more stable, have better thermal stability, and also it has a better morphology surface. And next one is the photodetector. And using titanium dioxide as a photodetector material is because titanium dioxide is an intrinsic n-type while indirect bandgap metal oxide semiconductor. And we're using titanium dioxide to make the nanotube as a one-dimensional structure because they have a very large active area. And you can see here, we're using electrospinning and to deposit the titanium dioxide material on the silicon dioxide. And then we drop some perovskite solution on our substrate. And then we spin coating and at the D, you can see we baking at the 100 degree and with the low pressure. And the perovskite will deposit on the substrate. And then we use this to fabricate a device, a photo detector device at here at the right side. So this is a photo detector part. And we're going to introduce the solar cell part. So we're going to talk about two kind of the solar cell. The first type is the dye-sensitive solar cell, and also called DSSC. So in DSSC, we have the five main components. The first is two glasses substrate with the ITO or FTO layer, and the mesoporous semiconductor metal oxide layer, like the titanium dioxide layer, like right here, you can see in the left figure, like here, and the other is the single layer of the dye molecule, and the fourth is the iodide electrolyte content iodide electrolyte container redox pair. And the other hand, we have the electrolyte for the platinum counter electrode. So the the photoanodes in DSSC include the titanium dioxide nanoparticle, and it was found that the performance of the DSSC can be improved by to make our titanium dioxide to have better porosity, and then we can improve our efficiency of the DSSC. So titanium dioxide is a very important part of the DSSC. So here we are going to talk about the perovskite solar cell. The perovskite solar cell, we mainly using the titanium dioxide, not like the previous one we talked about. We're using the titanium dioxide in perovskite. It's not like anode. We're using titanium dioxide to promote our surface and make the perovskite layer and the FTO or ITO layer to contact better. So we adding the titanium dioxide layer to make sure we have a better surface. And then we are going to talk about the photocatalytic. And so first of all, we're going to about how it works. The catalytic surface electron absorb enough energy to detect by the irradiating UV light or sunlight. And a positive charge electric cavity is formed where the electrons separate. The electric hole will oxidize the hydroxide group free of the nearby water molecule, make it a very active hydroxide radical. Once the hydroxide extremely encounter the organic matter, it will take the electron back, and the organic molecule will fall apart due to the collapse of the bond. And in 1972, the Professor Fujishima of the University of Tokyo, who discovered the photocatalyst, and so this discovery is known as the Fujishima effect. So let's talk about, and next we can see there are a lot of different applications of the titanium dioxide as a photocatalyst, and we can see like NOx decomposition and like maybe dirtiness prevention or antibacterial, and also the water treatment. And here is my reference of the titanium dioxide application. And last one is the titanium dioxide application in our daily life. And here you can see like the ink of the pen, and also the correction fluid or the sunscreen component. and also like the cosmetics is using the titanium dioxide too. And finally, we are going to talk about our summary. And first is titanium dioxide is an environmentally friendly optical semiconductor material. And secondly is titanium dioxide is considered to be promising in semiconductor field like a solar cell, wireless charging pad, or uh, motherboard chips and the LED lighting, and also DSSC. And third is titanium dioxide considered a promising semiconductor for a lot of reasons, like a stable, insoluble in water, and safe and non-toxic material. And with a good structure and mechanical property make it suitable in different applications. And the last one is the safety of using titanium dioxide for daily life has been proven in the commercial product like sunscreen, like the toothpaste and cosmetics. And so this is our summary. And last one is the member contribution. And the first one is Zhang Shuyu. He doing the introduction and the properties. And second one is me, Yi Changru. I made the application part. And the third one is the Guo Yuguang. He made the characterization. And the fourth one is Zhang Yuxi. She made the synthesized method and the scale up process. And the last one is Angelina. She made the characterization and the semiconductor companies. And thanks for your listening.